Hi, this is Chintan Patel. In this lecture, we will see few concepts of the elastic constants. There are a lot of definitions and the new terms that are going to be introduced in these lectures. So we will start with the first definition, and that definition is nothing but the linear strain. Because we are going to introduce the Poisson's ratio, and the Poisson's ratio is made up of the two different definitions, and that's why you need to understand first what are these two new definitions for you. Basically, you know the value of the strain, or what is the strain. Strain is nothing but the change in length upon original length. We all know that ratio, and that is the unitless quantity. We also know that. But there are two types of the strains. One is the linear strain and the second one is the lateral strain. Now, what are the main difference between them, and that is also explained in it by the definition. So if you see the definition of the linear strain, it is the ratio of the change in linear dimension to the original linear dimension of the member. Now, what are the linear dimension? You can say that the member is having the different types of a dimension in different direction. Let's say if you are considering the 3D member, then the 3D member may be put into the three reference axes, that are the x, y and z. If your member is having the maximum amount of a dimension in the x direction, let's say its length is in the x, direction, then that particular maximum dimension direction is known as its longitudinal axis, or its axis basically. So whatever the dimensions are along its axis are known as the linear dimensions. So whenever for example, you are considering a object which is rectangular of the bar like this, and if you apply the pull force on it, then the length will be increased, and that increase in the length is known as a linear increment, or the strain which is constituted from that particular increment of that length will give you the answer of the linear strain. The answer of the linear strain can be formalized by the simple equation of the strain, that is nothing but the delta L upon L. Okay, so now we will move on to the next definition. Another definition which is used for the Poisson's ratio that is known as a lateral strain. Now, what is lateral strain? There is only small difference between the linear strain and the lateral strain. The definition itself indicates that difference, that is it is the ratio of the change in lateral dimension to the original lateral dimensions of the member. Now, what are the lateral dimensions? As we have already defined the linear dimensions, the dimensions which are along the longitudinal axis, those were the linear direction. Now, what are the lateral dimensions? All the dimensions perpendicular to the axis of the member, all the perpendicular to the longitudinal directions are known as the lateral dimensions. Let's say we have considered our axis of the member in the x direction. So the dimension in the y direction and dimension in the z directions are known as the lateral dimensions. So any change in that y or a z direction will give you the answer of the lateral strain. Consider this very important topic. When you apply the pull force on the body which is in the longitudinal direction, okay, then the length in the longitudinal direction will increase, but the volume is constant, and that's why two lateral dimension, its height and its width, both are going to be contracted, and that's why the lateral strain will be negative as compared to the linear strain. So these two strains types should be clear for the definition of the Poisson's ratio. As you can see in this diagram, we have taken an example of the circular bar in which the pull force P is applied on this bar. Then the length may be increased, that is represented by the L plus delta L, but the diameter of the bar will be reduced, that is nothing but the lateral dimension which is going to be reduced now. Okay, so now we will define our main first elastic constant, that is nothing but the Poisson's ratio. Now, what is the Poisson's ratio? Definitely it is kind of a constant, and that's why we are introducing it in this chapter. So the definition says that when a homogeneous material is loaded within its elastic limit, the ratio of the lateral strain to the linear strain is constant, and that constant is known as a Poisson's ratio. We might see this mathematical form of this definition, that is nothing but the lateral strain upon linear strain, that is constant, and this constant is known as the Poisson's ratio, which is denoted by 1 upon m or mu. So these are the different types of notation which can be used in your examples. So these notations are represented by the equation as shown in below, that is lateral strain equals to 1 by m epsilon equals to mu into epsilon. Now what is epsilon? Epsilon is nothing but the linear strain. So epsilon and lateral strain can be denoted as an epsilon dash. Okay, so this was our Poisson's ratio, which could be asked in a 1 to 3 marks, and you have to explain it based on the this slide in your examination. So we will now move on to another definition of this chapter, that is nothing but the volumetric strain. This is another kind of a strain. As the name itself indicates that the strain is concerned with the volume or the change in a volume, and that's why we can directly convert it in the basic definition of the strain into the volumetric definition of the strain. That is nothing but the ratio of the change in volume to the original volume is known as a volumetric strain. If we neglect the 1D or a 2D members, then we will most probably in a day-to-day life we will have to face the 3D member stress conditions. As we all know, the volume of the member should be constant, and that's why whenever you apply the force or the member is subjected to the force in a particular one direction, then its dimension is going to increase in that direction, but its other dimensions which are in the lateral direction are going to be contracted or reduced, or they might be in the contradictory with the previous dimensions. Okay, and that's why we need to consider the volumetric strain, that how much volume is going to be changed due to this application of the force or application of the stresses, and that's why we are going to find out the volumetric strain. As we all know that the mathematical form of the volumetric strain is represented by or denoted by epsilon V, and epsilon V is nothing but delta V by V. Delta V is changing volume upon V is original volume. So this is the equation of the volumetric strain. So now we will move on to the next topic of this lecture, that is the derivation. Now what derivation we are going to focus over here, that is the derivation of the formula to determine the volumetric strain. Now volumetric strain is the major concern which we need to find out for the particular case. Which case we have considered over here? We have considered the case of a rectangular bar. Okay, we have considered the case of a rectangular bar. So what would be the volume of that rectangular bar? That can be represented as a V equals to LB into T. Now we know the volume of the rectangular bar is nothing but the V equals to LB into T. Now what we will do, our intention is to find out the volumetric strain. So in order to find out the volumetric strain, we need to calculate the delta V. How we are going to find out this delta V? By the partial differentiation. We are going to find this delta V by the partial differentiation. So delta V is nothing but the partial differentiation with respect to length, then the B into T will be constant, plus partial differentiation with respect to B, then L into T will be constant, and partial differentiation with respect to delta T, then B into L will be constant. Okay, so now our intention is to find out the volumetric strain. Now what is the volumetric strain? Volumetric strain is nothing but the delta V by V, and that is our intention, and that's why we have divided the upper equation. We have divided the upper equation by the original V. So if you divide this equation by the original V, then it can be written as a V can be written as a LBT. Okay, so if you divide this LBT denominator into individual numerator, then individual division will give you the simplified form like this. This is our simplified form, where the B into T is cancelled out in the first term, then in the second term L into T is cancelled out, and in the last term L into B is cancelled out. Okay, so this term is nothing but the delta V by V is EV. EV is EV can be represented as a epsilon V. This is nothing but a epsilon V. This is Ex, that is the strain in the x direction or in the longitudinal direction, that is nothing but the epsilon x. This is also epsilon y and epsilon z. So we have introduced the equation, or we have came across the equation of the volumetric strain, which is the summation of the different types of a strain in particular directions, in the three mutual perpendicular directions. So the epsilon V is nothing but the summation of the epsilon x, epsilon y and epsilon z. Now as we can see, the volumetric strain is the algebraic sum of all the axial and the linear strain. Now to calculate the volumetric strain, we will consider the three different cases. Now what are those cases? Let me explain it. The first case is nothing but the uniaxial case. Okay, so the first case is uniaxial loading, where the load is applied along only one direction. The second case is the biaxial loading, where we apply the load along two different perpendicular directions, that let's say for in x and y direction, or y and z direction, or x and z direction. Our next type is the triaxial loading, or that is known as a 3D state. Okay, so in which we will consider the three mutual perpendicular direction loading, x, y and z. Okay, so we have calculated for each and every cases, for three different cases we have calculated the volumetric strain equation, and that equation will be directly utilized in our examples to solve the 7-marker example. So we will see that equation in the next slide, and that formulas are nothing but the first one is the rectangular specimen, uniaxial loading, and uniaxial loading, that means sigma y and sigma z is equals to 0, because we are subjected to only sigma x. As you can see, the epsilon v or EV is nothing but the delta V by V, that is sigma x upon E into 1 minus 2 mu, because here only one stress is available, and that's why we are considering only sigma x. Similarly, if you consider two-dimension loading or a biaxial loading, then the equation will be the same, but the only thing will be changing, and that thing is nothing but the sigma x plus sigma y. In above equation, there was only one stress available in the one direction because it was the uniaxial loading. But in this case, due to the biaxial loading, we will consider two different stresses in the two different directions, and those are nothing but the sigma x plus sigma y. Now the rest of the equation is the same. Now the third condition, third case, which is nothing but the rectangular specimen which is subjected to a triaxial loading, and in this triaxial loading three different stresses should be considered, and the equation remains the same unless only one term is changing, that is instead of the sigma x and sigma y, we are considering the summation of sigma x plus sigma y by sigma z. Okay, so this was our last term which is changing, and due to this change we will we can easily remember these three different equations for the example point of view. These three equations should be remembered thoroughly in order to solve the example easily. Okay, so this was very nice. Now we will move on to the rest of the definition of this lecture, and those definitions are nothing but the bulk modulus. Now what is bulk modulus? To define the bulk modulus, let me give you first a situation where where the body is subjected to three mutual perpendicular loading. Now three mutual perpendicular direction are applying the forces or the stresses on the body, then with the equal and if the intensity of those stresses are equal, consider that the three mutual perpendicular stresses are acting on the body in three different directions but with the equal intensity. then the ratio of the direct stress to the corresponding volumetric strain is known as a bulk modulus, which can be denoted as a K. Now, if we want to find out the mathematical form of this bulk modulus, then it can be written as K equals to direct stress upon volumetric strain, and direct stress is generally represented by the sigma, and divided by volumetric strain is nothing but the delta V by V. So this is the basic definition of the bulk modulus. Bulk modulus is also asked in your examination so many times, and in examples you will have to find out the value of the K in order to find out the different elastic constants. Now we will see our last definition, that is nothing but the shear modulus or modulus of rigidity. Now shear modulus is somewhat similar to the Young's modulus or modulus of elasticity. So both are similar, but the only change is that, as you can see in the definition, that is the within the elastic limit, the shear stress is directly proportional to shear strain. In the case of the elastic constant, we were using this that the normal stress is directly proportional to normal strain, but in this case we are considering the shear stress instead of the normal stress. Okay, so that is the only change. The rest of the definition is somewhat dissimilar to the elastic constant, elastic modulus or modulus of elasticity or Young's modulus. So if you consider this condition in which within the elastic limit the shear stress is directly proportional to the shear strain, then the ratio of the shear stress to the shear strain is known as a shear modulus, which can be denoted as C or G or N. Those are the different notation for the same constant, that is nothing but the shear modulus or modulus of rigidity. So tau upon phi, phi is nothing but the shear strain, so tau upon phi is represented as a C or a G or N, and those are nothing but the shear modulus or modulus of rigidity. So those are the definitions and the new terms which you need to remember before starting the examples, and the equation which I have already formalized in this lecture should be remembered in order to calculate the example very smoothly. So in the next lecture we will see few more derivations, and after that we will see one example in order to explain the procedure so that you can understand the examination pattern. Okay, so we conclude our lecture over here. Thank you.